Welcome to our lecture on deep learning. In the last lecture we discussed stochastic gradient descent methods, and we said that it is important to adjust the learning rate. We also touched on the topic of preconditioning as a means to adjust the learning rate per gradient dimension. Today we go a little bit deeper in this topic and discuss methods for gradient acceleration. As a start, let's look at an example. So we have a two-dimensional function f of x equals 0.1 times the first dimension to the squared and 2 times the second dimension to the squared. We see that there are very different weights applied to these two dimensions. 0.1, a small weight to x1 squared, and 2 to x2 squared, so a larger one. One effect of this unequal weighting of these two dimensions, x1 and x2, is that small changes in x2 already change the function value a lot. Thus, the gradient is heavily influenced by x2. If we do gradient updates, we're moving a lot in this x2 dimension, and we're not moving very much in the x1 dimension. This results to an oscillation here in our optimization and very small steps in x1. So we need many steps in order to converge. Now this is with a learning rate of 0.4. If we just increase the learning rate a little bit more, this problem does not only affect slow conversion or fast convergence, but it actually means that we will quickly diverge. So if you look at our previous example with the learning rate of 0.4, you already saw that we overshot. Now, because small changes in x2 already changed the function value a lot, it actually makes it much easier to overshoot in these dimensions. And with a learning rate of 0.6, we very quickly diverge. So if you look at these values here, we have ranges between -1000 and 1000. Thus, what we would like to do is we would like to adjust the learning rate in different ways in the different dimensions, depending on the problem. Namely, we want to apply, for example, preconditioning methods. One idea to address this problem is by introducing so-called momentum to the gradient. It solves this problem by introducing a velocity vector denoted v at little t for each time step t. Vt in each iteration is updated as gamma times the velocity vector from the last iteration t minus 1 plus our learning rate eta t at time step t times the gradient at time step t. So we have this additional momentum hyperparameter gamma that is between 0 and 1. And now once we have the velocity, which already contains information about our gradient, we do update our x as our previous x at time step t minus 1 minus the velocity. As a result, the gradient will have information about previous gradients because the velocity accumulates the gradient information. Now, if we look at the same optimization problem as before at the same learning rates, then we see that for the learning rate of 0.4 with a gamma of 0.5 in the beginning, we are doing the same update. However, because we are keeping information about past gradients, we are not oscillating around that much and rather making more progress in the other dimension. At the same time, it also reduces the risk of overshooting and diverging using momentum. You see that at the learning rate eta of 0.6, where we diverged without momentum, in this case, we're still arriving at the optimum. To get a better understanding of what momentum does, let's ravel this recurrent computation that's actually happening in the velocity variable over time. V at time step t is computed as the learning rate at time step t times the gradient at time step t plus gamma, this number between 0 and 1, times the velocity at the previous iteration t minus 1. And this, of course, is recurrent, so we can further expand it as gamma times the previous gradient information of the iteration t minus 1 plus the previous velocity vector. Now if we expand this all the way back to the first iteration, then we see that the velocity vector is a weighted average over all the gradients that we computed so far, back to the first iteration. Vt is a weighted sum over all past gradients multiplied by the learning rate at that dimensions and also by a power of gamma. So because gamma is smaller than 1, gamma decreases with each multiplication with itself. So the higher this power is, the smaller this value gamma will be. So we have an exponential decay. So the weights decay exponentially with a speed that is controlled by gamma. So if we set gamma to a value that is close to 1, then the speed is slower than if we set gamma to a smaller value, such as 0.6. In the extreme case, if we set gamma to 0, then we just get our normal gradient descent back. So this would correspond to having no velocity at all. Momentum smoothes our updates to the weights over time. If we set a small value for gamma, then this weighted average will focus more on the very recent gradients. And if we set a large value for gamma close to 1, then it will look further in the past and smooth this more. As a result, it may help to walk out of regions where the gradient is relatively flat. Also note that because the sum over all these gamma values is 1 plus gamma squared and so on and so forth, because the sum equals 1 divided by 1 minus gamma, it results that if all the gradients are always similar to each other, so if eta at time step t times the gradient at time step t can be approximated by eta times g for all time steps, then the momentum changes the weight updates from eta times g to eta divided by 1 minus gamma times g. So let's summarize momentum. Momentum uses an exponentially weighted moving average of the gradient to perform our update. It takes the weighted average over all past time steps with weights that decay exponentially by the time step. And it helps to smooth the independent variable updates for adjacent time steps in the direction, which can help with overshooting, it can help with moving out of flat regions. In deep learning, we typically reduce the learning rate over time according to some schedule. For example, we may say that the learning rate eta at time step t is given by the initial learning rate eta 0 divided by the square root of the time step t plus a smoothing constant. Now, in order to motivate the next gradient acceleration method, let's say that we have a learning problem where for some of the weight dimensions we observe very little gradient information most of the time, and only very infrequently we actually observe, for example, a training example where this feature becomes relevant and the gradient becomes large. An example might be that we're training a language model, and language models are sparse in the words. So it may be that most of our sentences or our text features don't contain most of the words. However, sometimes an important keyword pops up, and then the gradient for this word feature becomes suddenly large. Now, if we apply the standard weight decay, it may happen that if this feature appears too late, that we cannot make much progress anymore in this dimension. A more adaptive learning rate decay would be appropriate for this problem. And AdaGrad addresses this issue by tracking only the aggregate of the square of the partial derivatives for each dimension. So if the feature doesn't appear very frequently, then most of the time this will be 0 or close to 0. However, sometimes it becomes large. Thus, the aggregate would still stay small. However, for a feature that appears very frequently, where we always observe a gradient in this direction, this aggregate would grow faster. And this allows us to keep track of the different dimensions that we have already updated a lot and the ones that we haven't updated a lot. Let's further look at an example where we have a two-dimensional optimization problem here. So we have f of x, where x is a vector that has x1 and x2. And now what we are computing in each iteration is the gradient of f with respect to x. So we are computing the two partial derivatives, df dx1 and df dx2. And we're updating in each iteration the corresponding entry in x with the last value minus eta times this partial derivative for this dimension. Now, whenever there is a big difference in the gradient values for x1 and x2, a small learning rate would be needed to avoid a divergence in the larger gradient dimensions, as we have seen in our slanted optimization problem. Now, as a result, the independent variables will move very slowly in these dimensions with smaller gradient values. AdaGrad also addresses this problem by adjusting the learning rate according to the gradient values in each dimensions, as it accumulates these in one variable. So AdaGrad readjusts the learning rate of each parameter using the cumulative variable st, capturing the square of the gradient dimensions. So st in each iteration is computed by the previous st minus 1 plus the Hadamard product of the gradient at time step t with the gradient of time step t. So that means that we're taking the gradient vector, say that's g1 through gd times itself, and the Hadamard product yields a vector of the same size. That is the pointwise product. Of these, so we are getting as entries the squared of the entries in the gradient at time step t. And given this cumulative variable st, we are reweighting the gradient in each update. So xt is updated as the previous point, xt minus 1, minus eta, the learning rate, divided by the square root of st, this aggregate variable, plus epsilon, again, the pointwise product of this times the gradient. Now this is a slight abuse of notation because we are applying pointwise operation to a vector, which means that we are applying it to each element. As a result of this, we are essentially dividing each element of gt by something that is close to the square root of the sum of squares of all the gradients. Eta here is a constant that maintains numerical stability, so it's just a very small number. And at time step 0, we would initialize S0 to 0. To go back to our language model example, if we are observing one word very infrequently, then we are dividing by a smaller number than if we are observing another word very frequently in each iteration. Or in our example with the two features with unequal weights, we would get used to always getting smaller gradients in one dimension and thus upweight these features compared to another feature where we're always seeing large gradients. So for elements of the gradient that have a constant and large partial derivatives, the learning rate will drop faster. So we will downweight this more. And you can think of this also as a way to decay the learning rate over time, because S is always growing over time. We're always adding the next square to S. Yeah? If the partial derivative, however, remains small, then the learning rate for this dimension will decline more slowly. However, still the learning rate for each element declines in each iteration. So this is a form of decay. The learning rate declines very fast during the early iterations and slower over time. The problem of Adagrad is that it might have difficulty finding an optimum because the learning rate will be too small at the later iteration. So this is still a limitation of Adagrad. Let's look at our previous example of this very slanted function where we have two features, x1 squared, x2 squared, and we are applying a small weight 0.1 to x1 squared and a large weight 2 to x2 squared. So it's very slanted, and one thing that Adagrad does much better is that it produces a much smoother trajectory that points very much towards the minimum. However, already with a learning rate of 0.4 and due to the cumulative effect of ST, the learning rate continuously decays, and it decays actually so quickly that at some point we're making extremely small progress here. So we're not reaching this optimum. Now with a larger learning rate, in this case, this fixes the problem. It also reduces the chance of overshooting here, as we're seeing. However, it's still a limitation of Adagrad that it leads to quick decays of the learning rate. So let's summarize Adagrad. It constantly adjusts the learning rate during each iteration to give each element in the independent variable of the objective function its own learning rate. When using Adagrad, the learning rate of each element in the independent variable decreases during each iteration. And it might have difficulty finding a useful solution because the learning rate will be too small at later iterations. A method that modifies Adagrad in order to solve this issue that the gradient decays so quickly is called RMSProp. RMSProp also introduces this variable st. However, it computes it differently. So remember before in Adagrad, st was the sum of squares of the gradient entries. Here it is computed as an exponentially weighted moving average of these squares. So in each iteration st is computed as gamma, where gamma is a hyperparameter between 0 and 1. So it's a number that is smaller than 1 times st minus 1 plus 1 minus gamma times the squared of the gradient. So we're in each iteration building a convex combination of the previous s vector and the squared gradient vector. And then RMSProp readjusts the learning rate as it's done in AdaGrad. So xt, our next parameter estimate, is computed as the previous xt minus 1 minus eta, the learning rate, divided by the square root of st, this exponential weighted moving average of the squares of the gradient elements, plus epsilon, where epsilon is a small constant added to maintain numerical stability, times the gradient at time step t. Now let's look at this exponentially weighted moving average by expanding the definition of st. So st is computed as 1 minus gamma times the squared gradient plus gamma times s at the iteration t minus 1. This can again be expanded to get an expression in st minus 2, because it's still 1 minus gamma times the squared gradient plus gamma times the squared gradient at iteration t minus 1. And if we expand this st all the way up to the first iteration, then we're seeing that we're getting 1 minus gamma plus the gradient at time step t squared plus gamma times the gradient at time step t minus 1 squared plus, and so on and so forth, up to gamma to the power of t minus 1 times the gradient at time step 1. And as gamma is now a number that is smaller than 1, we're getting an exponential decay in the gradient that we're adding here. And again, if we apply a smaller value for gamma, then the decay will be faster than if we apply a larger value of gamma. And because the series 1 plus gamma squared and so on goes to 1 divided by 1 minus gamma, the sum of the weights always equals to 1. So here we see a large weight of gamma, and here we see a small weight of gamma. And the sum over, well, this discrete line here is always equal to 1. If we go back to our two-dimensional function, f of x equals 0.1 x1 squared plus 2 times x2 squared, then we see that we get the same benefit as before for AdaGrad, also for RMSProp, here with a value of gamma equals 0.9, this exponential decay rate. And if we compare it to AdaGrad, we see that we get similarly a smooth trajectory for optimization. However, we do arrive at the optimum because it doesn't decay so fast. So in contrast to AdaGrad, RMSProp approaches the optimal solution faster at the same learning rate, eta equals 0.4. And the difference between these two methods is that RMSProp uses an exponentially weighted moving average on the squares of the elements of the gradient instead of just adding all of these up. The next method that we will look at is called AdaDelta. Now AdaDelta adds an additional exponentially weighted moving average to our ST. So it keeps track of two EWMAs, namely ST and delta XT. As before, ST is an exponentially weighted moving average on the squared of the gradient entries, where we are using the parameter rho to conform with the notation of the original paper. It additionally uses this delta t, which records an exponentially weighted moving averages of the squared of the steps that are being done g prime. So what is g prime? G prime at time point t is set to the square root of our delta xt minus 1 plus e. E again is a small constant, such as 10 to the minus 5, that is just there for numerical stability purposes. Divided by st, our exponentially weighted moving average over the square of the gradients, time point t, again plus e for numerical stability. This whole thing then is pointwise multiplied by our current gradient, which yields our gt prime, and our gt prime is then used to update our parameter vector x. So x at time point t is computed as x at time point t minus 1 minus g prime at time point t. And delta x is now an exponentially weighted moving average on the squares on these update steps g prime. Delta xt is rho times delta x t minus 1 plus 1 minus rho times the squared of g prime at time point t. Rho here is a counterpart to gamma in RMS prop. Now one observation here is that this expression here for the update doesn't contain a learning rate. However, the learning rate that we had in RMS prop, eta, has been replaced with the square root of delta x t minus 1. So it's an algorithm that tries to completely remove the problem of finding a learning rate, well, instead of still introducing a hyperparameter, so there is no free lunch. Finally, the last method that we will look at is so-called ADAM, which uses momentum vt as the exponentially weighted moving average over the gradient. So vt, our momentum variable, is computed as beta 1 times vt minus 1 from the last iteration plus 1 minus beta 1 times our gradient at iteration t, where beta 1 is a number between 0 and 1, and the author suggests to use the value 0.9 here. St again is an exponentially weighted moving average over the squares of the elements of the gradient. So St is set to beta 2, which is another parameter between 0 and 1, and here the author suggests to use a number that is very close to 1, namely 0.999 times St minus 1 plus 1 minus beta 2 times the squared gradient. Both v0 and s0 are initialized as 0, and for this reason vt is equal to 1 minus beta 1 times the sum from I equals 1 through t of the powers of beta 1 times t minus I times the gradient at iteration I. So for example, if we look at beta 1 equals 0.9 and v1 equals 0.1 times the gradient at the first iteration, then the sum of the weights from all these previous time steps will become 1 minus beta 1 times the sum over iteration I from 1 through t, beta 1 to the power of t minus I. Now if we multiply this out, we're basically getting the sum here minus the same sum times beta 1, where if we remove all the duplicate terms in these two sums, we're left with 1 minus beta 1 t. Thus, for small iterations t, the sum will be small. And this creates a bias in both vt and st, and Adam corrects for this bias by computing an unbiased version, vt hat, as vt divided by 1 minus beta 1 t, and similarly computes st hat as st divided by, well, 1 minus b2 to the power of t. So analogous to as we did for v. And now these bias corrected variables vt and st hat are used to readjust the learning rate of each model parameter. Our update g prime at time step t is computed as eta, or learning rate, times vt hat divided by the square root of st hat plus a small positive constant for numerical stability, for example, 10 to the minus 8. Finally, this update g prime t is used to update our parameters. So the parameter vector xt is updated to xt minus 1 minus g prime at times 2 at t. So Adam combines the ideas from RMSProp with a exponentially weighted moving average on the mini-batch stochastic gradient descent, and it introduces bias correction. So to wrap things up, we have learned that the magnitude of the learning rate matters, and there may be a reason to adjust the magnitudes of the learning rates and different schedules to each dimensions of the gradient. And the rate of decay is just as important to just the magnitude. So we have discussed various methods that use, for example, the exponentially weighted moving average or other things to keep track of past information. And with this, I want to say goodbye and see you next time.